Hey, this is Lance Nichols with High Altitude Ballooning Part 4, Communication. So why do we want to communicate? There's two reasons. One of them is we want to be able to control our balloon, and the two things that we want to control, really we want to control the flight. That's usually the primary focus. You want to maintain control of the balloon. So this can be, flight termination, your vents, valves, ballast, stuff that, you control your altitude with. And then also maybe experiment control, like let's say you wanted to take a sample at a certain altitude or something. So you could open the capsule and then close it again using control through communication. And then live data. So sometimes we want live video for the Eclipse projects. So that's definitely one of the reasons that we would want live data. But also location and other sensor data, so we can, theoretically, you could make scientific decisions and then also flight decisions using this live data. So you can be like, okay, we are here, we should terminate the flight so we don't, pose a risk, or maybe there's an easier recovery or something like that. So that's why we communicate. So we communicate through the satellite using the Iridium modem. As one of the ways that we communicate. So the Iridium has 3 bits of latched control data. So this is data that we control the payload with. And then there's a 30-second to 10-minute delay from when we send the command, send the state of these 3 bits to it, and it actually gets received because it has to go through quite the system, which we'll see in a minute. And then we have 4 bits of return data that comes back at that same rate as well. So we can send basic commands using the Iridium. We also have point-to-point communication. So these are some of the systems that we use, RFD 900 and LoRa. These are kind of mid-bandwidth data transmission. You can send pictures, sensor data, you could transmit location. But the thing is that, with all of these, there's some directional aspects. So if you can see these antennas here, so these are being pointed at the balloon. We have active tracking capabilities, so we can follow the balloon while it's in flight, given its location. And it's important for the RFD 900 and LoRa, but it's especially important for the ubiquity modems because we are it's a point-to-point network, so we're making a LAN that basically both the balloon and the ground station are on. This is pretty high bandwidth. We can send live video, images, everything else you could tack on there to temperature data, location, stuff like that. So understanding Iridium payload commanding. So commanding overview here, you can see kind of the information transmission stack here on the right. Starts down here at the bottom. We send a command, goes through the internet, through the satellites, through the XBee network to the endpoint device. So usually we want to tell our payload to do something, and we want to be able to do that on the ground. So the important components here that we really have control over are the Iridium modem and the XBee radio network here. So obviously we don't have our own satellites and we don't control the internet. So we have our own computer, we have this physical device, and we have basically everything up here. So let's talk about the XBee radios. So we use these XBee devices. You'll primarily see both of these devices in our lab here. We have the XBee3 SMT, surface mount device with the castellated pins on the side. You can use this one as a simple microcontroller, and I believe you can also program this one as a simple microcontroller as well, but we use this one as well. These are 3.3 volt devices, and we program them with XETU, so the radio component, and then we use MicroPython for the microcontroller component. So that they're simple microcontrollers, so they have some drawbacks that you should definitely look into if you are planning to use them as a microcontroller. They have strange behavior on some of their pins. They don't have interrupts, so yeah, their timing is weird. So definitely know their limitations before you dive in on using them. Basics of an XBee network. All devices must be on the same network name, known as a PAN ID. So basically everything is sharing the same name, so or channel, so everything knows that they're all communicating with each other. There must be one and only one coordinator. So think of the coordinator as maybe like your access point or your router or something in a network. So it kind of creates the network. It lets devices know that there is a network to join. It keeps track of the devices on the network, stuff like that. There are mesh network topologies for the XBee devices as well, but we are not using those topologies. We're using the coordinator topology. So decently low bandwidth data transmission, but quite a bit in comparison to the Iridium, and then usage range of around 100 meters. So this is just a local radio network inside of the balloon, payload chain. So it's just kind of a little local radio, so you don't have to run wires everywhere. The Iridium Assembly is made up of 3 parts. We have the XBee. This is the kind of middle device that you saw before. It has pins. This is set up as the coordinator in the network topology. And then we have the Occam's board, which is a green board here. And then we have the Iridium modem, which is under here. The Occam's board kind of sits between the 3.3 volt XBee radio and the 5 volt Iridium modem, and basically serves as a mediator for that communication. The Iridium modem has 2 antennas, one for GPS and one for Iridium. And it's a 5 volt device, and really it's a black box, and we can manipulate the pins on the outside, but we have no control over it on the inside. So it's doing its thing, and it's not like something we can program. So there is bandwidth in the theoretical sense associated with the Iridium. It has these 3 bits that can have quite this delay on them. So it's not bandwidth in megabytes. It's like bits per minute or something. So it's not it's not something you can transmit any large amounts of data through. So you have to be careful. What you're trying to do. And then we should get a packet back every 10 seconds. So because of this really low bandwidth, we have a state system. So one state at a time. So we have a state that we put the Iridium in with a command. So you might think a command like, oh, hey, I'm yelling at you, hey, turn on the light. It's more like I'm turning on a light that tells you to turn on the light. And the light, I just flip the switch and then it's on. It's not like, hey, turn it on, and then I'm done talking, right? So it puts it into a state. And because the XBee network is downstream of this bottleneck, basically, in the Iridium infrastructure and Iridium Assembly, I'm not really sure where it is, but because of the black box nature. But because it's downstream of that, it also basically exists in this one state at a time because it is downstream of that. Despite it having, quite a bit higher bandwidth. So since we have just these 3 pins, these, pins can be either high or low. So we get 8 states out of that. So this is kind of what you would typically see on a command list that could be generated for a flight. This is like something I would generate. You can see, okay, hey, we have the idle state. So that's pretty typical with what we do. So that's like, oh, we can put it in this state and it's not telling it to do anything. And it just sits there and is idle, basically. And then we have, a flight termination one. We have a valve, open, close, change the algorithm. You're telling it to do something, but you have to keep in mind, it's a state system. So, for example, the cut down, you can see once the cut down is sent, it's not going to just cut down over and over and over. It's actually going to cut down once and then stop. And then if you want to cut down again, you can reset it by sending the idle. And then once the idle is received, then you can send cut down again. So you can't just like send cut down and then expect it to just go over and over and over. Because that's not what's going to happen. That's kind of the whole point of this presentation, is that you really need to understand this. The idle. So for example, if you send cut down and then you immediately send idle again, there's no guarantee that this will get interpreted in time. And it might just get immediately set back to 0, 0. So like for a millisecond, it might, oh, it's 1 and now it's 0 again. And then it might not see it, right? So yeah, like I mentioned, all of this is all the XBee network is downstream of the Iridium. So you have to, it basically has the same problem. It just gets propagated down. So we have once every 1 to 2 seconds, we're basically transmitting out to all the endpoint devices. Hey, this is the current state. 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 So that all of the devices know, hey, this is the current state, and they have the current state. So this is an example of kind of how it would propagate through the entire system. This is, say we're terminating the flight. So the idle state, let's just say, has been applied to the Iridium. So all of its pins are at 0, 0, 0. So we send double cut down. So we send an email command through the Iridium infrastructure. It takes some time, and then eventually it reaches the Iridium Assembly. And then it, sets these 3 pins here. What was it? 0, 0, 1, right? So then this Occam's microcontroller, or the XBee, if it happens to be the microcontroller, reads that in, transmits it over the XBee network, and then that's received, and then it physically cuts down, and then it cuts down, and then it stops, and then the microcontroller, whatever's controlling it, could be the XBee, I'm just going to point to this, will go, okay, I've cut down, and then it sets a flag, and it's like, all right, I have cut down, and I'm not going to keep trying to cut down. So it just happens once. But that said, this XBee will continue to say, hey, cut down. It's cut down state. It's cut down state. It's cut down state. It's cut down state. So, and this has to filter that out because of the state-based nature. And then let's say we have a 2-stage cut down confirmation. So once this is received, we're going to use these, these pins that go back down to the ground. We're going to use them to, give us a little bit more insight on what's going on, because the payload can be, really far away. So you can't really tell what's going on. So it can be useful to have some insight into what's going on the payload. So we can have 2-stage. So the first stage would be like, hey, once I get cut down, I'm just going to change the bits here. And then the other one is, once the cut down microcontroller has received cut down, it will send an acknowledge, and then that will update to a 3rd state. So you can see that here. So if you know what a state machine is, it's probably looks very, very similar to that. So we're kind of in the standby mode. So you can just kind of imagine this number here on the left of these boxes to be just the decimal number that's coming out of this 4 binary. So we're in a standby mode, nothing's going on, and then, hey, we received the cut down. So here, this is the thing that changes it. We received it, and if the state machine, there would be an arrow that wraps around and points back here for all other cases. But anyway, so we've received cut down. So this is 0, 0, 1. We got cut down, and then it goes, we can set this to 1. So hey, we know that the Iridium has got cut down at least. It got the command. And then once we get an acknowledge back from, it comes back through the XBee network to the microcontroller, then you can set it, it's 2. So now we received this, and we know that the endpoint device got it. So if it fails to terminate, then we go, oh, okay, so there was some problem with the actual termination. If you get a 1 and it fails to terminate, that's like, oh, there's something wrong with the communication between the Iridium, between here and here. There's something wrong with the communication here. So you can suss that out. Things can get much more complicated. So this is, I'm not going to go too in depth in this, but this is like a system that has 2 redundant cutdowns, and it also has temperature sensing on the flight termination. And the temperature sensing is important because we use, for some flight termination, we use nichrome wire. So basically you put current through this very thin wire, it gets very hot, and then you cut down, cut a string, whatever. So basically the same thing. Hey, received cut down. Hey, the endpoint received cut down. Hey, the endpoint received cut down, and the temperature has gotten hot. So we've tried to cut it. We've detected that the physical thing that cuts the balloon down has actually happened. And then over here is like, oh, this is the redundant system. So you can kind of have this. And then if you're very clever, you can also use the fact that you could make certain things latch and certain things not latch. So here, if you send idle, it goes back to 0 if it was this temperature spike. But if it was this temperature spike and you send idle, nothing happens. So you could use that to, obviously think through it and recognize the risks that you're taking in doing that. But if you're clever, you can get a little bit more than 8 bits out of it if you really, really need that for some reason. So these are the 2 takeaways, really. The Iridium is a state-based system. That's like the main thing you need to understand is the Iridium is a state-based system, and the XBee network reflects this. And because it's downstream of this bottleneck. That is all. So thank you for watching, and hopefully you enjoyed learning about this.